Hi linear algebra students. The aim of today's video is to prove Cramer's rule. So it's not something that I would ask out of you. So you don't have to memorize this proof or know how to do it. It's just there as a completeness, right? Just to make the course a little bit more complete. But that's it. Watching this video is non-mandatory. You don't have to make it part of your notes. So what is Cramer's rule again? We consider a matrix equation AX equals B. If the determinant of A is non-zero, then AX equals B has unique solution given by this. Okay, so det A1B over det A, det A2B over det A, det ANB over det A. Okay, where AIB is the matrix obtained from A by replacing the ith column of A by B, by the column of constant, which is B. Okay, so first of all, before starting the proof, we just need to define the angle of attack, and this is it. So angle of attack, let's put it this way. We want to prove that, so prove that xi, okay, so xi being the ith component of x, is equal to det ai b over det a. And if we are able to prove this regardless of I, then it will be true for all the components of x. So we will be done. So regardless of I. Okay, now how do we do this? The idea is to understand what is this matrix AIB. Okay, so AIB. Okay, so this is writing it as like a bunch of columns. It will be like A1, and I'm gonna write a little bit too much. Okay, or not even. I'm gonna write here. That's it. It's gonna have like AI minus 1, and then instead of so as I said, we replace AI by B, right? So actually, let's color code this. So replace AI by B. Okay, so here, this is the column that goes here. So, all right, then we have AI plus 1, and we continue like this until AN. All right, now here's the game. So, this right here will be A times X. So, all right, this will give us like A1 all the way up to AI minus 1. And then instead of B, we will actually use the A times X that's over here. Okay, so this will give you A times X. And now we will have here our AI plus 1 all the way up to AN. All right, from that point. Oh, yes, okay. So now look at this, okay? So we can actually say that A times EI. So this, remember, it's the standard basis vector. Okay, so this will be equal to AI, right? Where EI is ith standard basis vector. So in other words, what this observation allows me to do, it allows me to replace all of these. So instead of like A1, I will write A times E1. Okay? Now instead of AI minus 1, I will write A times EI minus 1. Then this stays as is, and then here I will continue. So in other words, I will make the matrix A appear everywhere, right? EI here like n minus 1. Okay, so as I can see, there's a mistake here. This should be n minus... Oh no, this is I plus 1. Okay, we're good. So this is I plus 1. So here, same thing. You have EI plus 1. And then you're going to get like AEN. Okay, so that's where we are at. Now, this is the definition of the following matrix multiplication. So in other words, as you can see, there's an A everywhere, right? And we're going to factor it out. So we're going to say, all right, well, this is the matrix A times the matrix that we have right here. So E1, then until EI minus 1, then X, then EI plus 1, so EI plus 1, all the way up to EN. Okay? And now what we're doing is we're taking the determinants on both sides. So I remind you that what we have here is AIB. Okay, I'm just going to write it over here. So now let's erase this. So if we take the determinant on both sides, that on both sides, okay? So in other words, we take the determinant of AIB, and this will be equal the determinant of this big thing. So A times this matrix, E1, EI minus 1, X, EI plus 1, all the way up to EN. Okay? And then the idea is to use the multiplicative property of the determinants to say that this is the determinant of A times the determinant of this matrix. So E1, EI minus 1. Okay? Then X, EI plus 1, all the way up to EN. Okay? Now, here's the big argument, okay? And unfortunately, you either kind of see it or you don't. And I'm going to try to justify it well. This determinant right here, so yeah, I don't want to use orange here. I will use red. Yeah, this is the red I want to use. So this determinant turns out to be xi. Okay, and here I will try to justify this with an example. Okay, so like just an example. Suppose that you have a 4x4. Okay, so suppose that what you want to do is to take the determinant of like E1, E2, X, E4. Okay, what is this matrix in reality? So E1 is the first standard basic vector in R4. E2 is this. Now X is simply going to be X1, X2, X3, X4. And then finally, we're having like 0, 0, 0, 1. So that is the determinant we're trying to calculate. Well, if we just do the cofactor expansion, across the third row, right? So we're doing, and I'm going to color code in purple here because if I color code in orange, you will not see well. But here goes, like plus, minus, plus. So in other words, you do the cofactor expansion across the third row. What are you going to get? You're going to get x3, okay, times the determinant as you cross the column, times the determinant 1, 1, 1, 0, 0, and then 0, 0, 0, 1, like this, right? So in other words, you're getting x3. Now, how do you know that you always get a plus? Well, it's simple. It's because you're always going to do a cofactor expansion using the entry that's on a diagonal, right? And these entries have the same like sign in the cofactor expansion. So that's why you're getting just xi. So right, this determinant, regardless of like how you write it down, this is just xi. And then the proof is basically done. Okay, so I'm just going to erase this. So what did we prove? Well, we proved that the determinant of AIB is equal to the determinant of A times xi. So if the determinant of A is not 0, it means that we can swing the determinant of A on the other side and get that xi is equal to the determinant of AIB here you go. Oh, I'm actually going to remove the outside bracket. So AIB over the determinant of A. Now, as I said, this is what we wanted to prove, because we proved that it is true regardless of I. So let's actually take note of that. Like, since it's true regardless of I, since it's true regardless of I, it's true for all the entries. It's true for all components of X. All right. So I hope that this was interesting. Now, as I said, you don't need to have watched this video. You don't need to submit it as part of your lecture notes. This is just for those of you that are interested to know how to prove Cramer's rule. Well, here you have it. So have a good one.